Okay, guys, welcome. Today we're going to talk about solving Diophantine equations, and with that, we'll talk about what's known as the extended Euclidean algorithm. Now, of course, by using the extended Euclidean algorithm, we're going to have to revisit the regular Euclidean algorithm. And of course, this is going to be the key to helping us solve Diophantine equations, right? Now, what we're going to do is we're going to compute the GCD of 34 and 40, but we're going to keep track of all the information as we go through. And namely, what I want to do is we're going to find out that we can write the GCD of 34 and 40 as some linear combination of 34 and 40. That's really what our goal is right here. Right? So let's go ahead and let's do that. So of course, if I want the GCD of 34 and 40, the first thing I would want to do is I want to write 40 as 34. I guess we can do that over here, right? So where this is coming from is that I'm writing 40 as 34 times 1 plus 6. And now solving for 6, I can write that as -1 times 34 plus 40, and that's what's coming here. Okay, so I'm still writing 6 as a linear combination of 34 and 40. Now, if we move to the next step, of course, we would switch this 6 and the 34. So we're just switching these two things in this next step. Now I'm going to write 34, right? Now my next step is to write 34 as a multiple of 6 plus a remainder. And that, of course, is right here. 6 times 5 would give me 30, and then add 4 would give me 34. And then, of course, rearranging for 4 would give me that this is 6 times the -5 plus 34. Okay, so now that's going to come here. Now, we wanted to write this as a linear combination of 34 and 40, and I've lost that right now. So what we're going to do is we're going to substitute for this 6 what our original expression for 6 was, right, which was 34 times -1 plus 40. So now what we have is we have a 34 and then minus 5 times a -1, so plus 5 times 34. So that's going to give us 6 34s. And then, of course, I have this -5 times 40. So now I can write 4 as 6 times 34 minus 5 times 40, right? And again, just note that we switch spots here, right? So now I have 4 written as a linear combination of 34 and 40, as well as 6. And now we keep going. So now 6 we can write as 4 times 1 plus 2. And of course, solving for 2, we get that 2 is equal to 6 minus 1 times 4. But now, of course, we can substitute for 6 and 4, right? So this 6 is becoming our 34 times -1 plus 40 again. And this 4 is becoming the 6 times 34 minus 5 times -40, so -5 times 40, which we found in the previous step. And then, of course, if we combine our like terms, we have -134 is here, -634 is here, so we get 34 times -7 here. Okay, and then for our 40s, we have 140 here, and then we have a -1 times -5, so plus 5 40s, so we're going to get a 6 times 40. Okay, then in the next step, we'll switch 2 and 4, just so that our smaller numbers first. And now, of course, what can we do? Well, now we know that we have 2 and 4. So now what we can do is now this will become a 0, because the remainder when you would solve this would be 2 times 2 plus 0 is equal to 4. right? So now we get that our remainder is 2, sorry, that our GCD is 2, and we've expressed this as a linear combination of 34 and 40, right? So we see that if we take 34 times -7 plus 6 times 40, we get 2. So we have a solution to this equation. 34x plus 40 is equal to 2, right? Which is the GCD of 34 and 40. Now, this version of the Euclidean algorithm is the extended Euclidean algorithm, and it helps us to solve these equations, right? Now, of course, we know that a Diophantine equation doesn't have to be equal to the GCD, but it has to equal something that the GCD will divide, right? So it can be anything times our GCD. Now, if we want to solve something that's not explicitly the GCD, we would first solve for the GCD, and we would get some pair x0, y0 that works. And then to get the solution for k times the GCD, we just multiply each coordinate by k. And that's where this is coming from. All right, so we're going to do another example. Okay, now, if we wanted to solve 57x plus 165 times y is equal to 1, first you would find that the GCD of both of these is 3. And since 3 doesn't divide 1, you don't want to waste your time. And of course, there's no solutions. Now, since we know that the GCD of 57 and 165 is 3, and that's what's sitting right here, we know that we can solve that. So let's go ahead and let's do it. Okay. So again, the idea here is that first what I want to do is I want to write 165 as a linear combination, or sorry, as a multiple of 57 plus a remainder. So it's 2 times 57 plus 51. And then if I solve for the remainder, if I solve for 51, I get that that's 165 minus 2 times 57, which is coming right here. All right, so at each step, we want to be able to write what we have in our parentheses in each step, in each coordinate, as a linear combination of 165 and 57. Now, in the next step, we switch just to keep a smaller number first. And now I want to write 57 as a linear combination of 51, or sorry, as a multiple of 51 plus a remainder. And if I do that, it's 51 times 1 plus 6. And then rearranging, we get that 6 is equal to 57 minus 51 times 1. Now, of course, remember that 51 we wrote as 165 minus 2 times 57. So that can go in here for our 51. And now when we combine like terms, we're going to have 157 and then minus negative 2 57s. So we'll get 3 57s. And then we just have 165 being subtracted, so then we'll get the minus 165 here. And again, this whole thing is 6. So now we'll switch both of these again, and we want to write 51, which is right here, as a linear combination. Sorry, I keep saying that. As a multiple of 6 plus a remainder, right? So that can be done 6 times 8 plus 3. And then solving for 3 would give us 51 minus 8 times 6. Well, 6 we can write as 3 times 57 plus 165. That's a poor color choice. Times negative 1. Let's see, I can highlight gray. That's kind of interesting. Okay, but that works. Okay, so then we have 6 we can write as 3 times 57 plus 165 times negative 1. And 51, we know that we can write as 165 minus 2 times 57. And this whole thing would give us 3. Now, of course, when we combine like terms, we have a 165 here, and we have minus 8 times minus 1 165s. So we're going to get 9 165s total. Okay, and then for our 57s, we have minus 2 times 57 minus 24 57. So it looks like we get minus 26 57s. Okay. And of course, now we can switch our 3 and our 6 again, but now we know we're going to end up with the 0. And if you really wanted to, you could write 0 as a linear combination of all that stuff, but we really have what we need, right? And we know that we can get 0 by doing 57 times 55 plus negative 19 plus 165. But the important information is here, because now we know that we can write 3 as 165 times 9 plus 57 times negative 26, right? And so we get that our original Diophantine equation has solutions x equals negative 26 and y is equal to 9. And of course, if our original equation instead was equal to 15, which is 3 times 5, well, then we would do the exact same thing that we just did, except for the last step, since our solution was negative 26 and 9, we just multiply each of those by 5, right? So then we would get that x is equal to negative 130 and y is equal to 45. All right. So that completes this video on solving Diophantine equations. I hope you enjoyed, and I will see you next time.